So my project for ELU was to work with this FPGA, this tiny thing here. I don't think you can see it well, but it's really small, but don't get confused, it can actually make you cry. Because the whole idea of this project is that we don't use open source, like these proprietary things that usually Xilinx or Texas Instruments sell you, and they put a nice editor on it. But we use open source tools, which is nice, and it's a great philosophy, but it's still a little bit like assembling stuff by yourself and kind of to take care of a lot of small details to build stuff. Kind of the idea is like to start, why would we want to do anything with FPGAs, and then go a little bit through this development kit, and then explain a little bit what the tool chain is and some stuff we did, and then at the end we can make a summary of like known like stuff we learn and what to do and what not to do. So first of all, if anyone is a bit lost of what an FPGA is, FPGA, it's a field programmable gate array. It doesn't say anything in the name that kind of gives a clue what you do with it. The idea is that you can build any circuit by pretty much using like standardized components, and then have a way of interconnecting them. You put that in a nice chip, and you have input and output, so you can actually activate a pin, and then through that you can program a circuit. So you, through some very specific programming models and languages, you say how you want your circuit to behave, and then there's a set of tools that kind of build that in hardware for you. And that is really cool, because when you have stuff on hardware, you can kind of forget about these latency problems that you usually have while programming. You just need to make an efficient circuit, and then stuff can be done. Like every clock cycle, you can have a pipeline, I don't know, processing some input signals, for example. Then for latency critical stuff, this is something that we could go and actually build some really fast processing stuff. And yeah, this board here, it's built by Quick Logic. This is called the Quick Feather. They're very original by naming stuff while naming stuff. The coolest thing is that they have this SoC here, which kind of has two things. One, it's a microcontroller, so it's a Cortex M4, and they also have an FPGA. So they're both in there. They're a system on chip. And then they put your stuff around so you can play with it, like microphones, buttons, and a lot of other, I think there's a flash memory over here and stuff like that. And the cool thing is, like, with this kind of setup, we could do stuff like machine learning, for example, on IoT devices. So when you need some specific or like intensive processing that can be done through hardware, then we can do it here. They actually sell one toolkit for machine learning, so that's kind of, I think, their business model, because this is a pretty cheap board compared to like FPGAs in the past. So this is like 50 euros for the FPGA and the microcontroller and the board, of course. And then let's kind of go to understanding what this open source thing is. So you have hardware description languages. So these are some programming languages where you specify how a circuit behaves. Usually you cannot do like, you know, the same kind of programming blocks that you have. They differ a little bit, but they're now pretty good, and they're higher level than they used to be, so that's nice. And with this, like, same description of the hardware of the circuit, you can build like proper or like unique actually chips that you can produce in mass and create products out of it. You can use it for FPGAs, for example, or you can do some verification and testing, which is always necessary in this kind of pipelines. So you have this thing in the middle which kind of connects both, but it's not as easy as simply compiling code, which just translates in binary code so that the processor can take it into its pipelines. we need to actually create a circuit, and we need to create then tell the FPGA how to build that circuit. And that is when it gets kind of messy. So this is kind of like the open source tool chain. It's one of the weirdest diagrams I've ever seen, but it's also the easiest way to explain it. So you have the supported programming languages. It's Verilog, System Verilog, and VHDL. This one's older one. Verilog is like the one everyone knows, and then System Verilog is like the premium version of Verilog. Then once you have like your source code, you need to produce something in the middle. So that first time is a synthesis. Usually when you program a circuit, you do it at a very high level, and you need to translate that into two things. So that's called an RTL description. So register, RTL. So it's, yeah, so register, transfer level. So it's something that is can be done only by flip-flops, logic, and that's it, like in a very standardized way. And then from that, you can actually need some tool that routes it, so it actually places the circuits and kind of know how to connect everything that it needs. And then this is needed, this is the input for an assembler. So this is pretty much something that translated to a binary stream of code that you can put into FPGA, and like you can flash that, and then we finally have our program running on the FPGA. The thing is different here that with this chip than other FPGAs, at least the ones I've worked with. This microcontroller that it has, this ARM core that it has, it needs to control the FPGA. So it's really hard to separate both of them, like the programming of the microcontroller, which you can actually use for your solution as well. Like you can use Zephyr, I think someone mentioned it, and it's what's been used here. And then you also need to put some logic to kind of interface with the FPGA. As far as I understood, you should not really have to go deep into like changing stuff in there when you create a new project, but it is kind of like overwhelming the amount of code that you need to do something very simple, at least for this. And one of the biggest pains I had in this project is that I use a Mac and nothing run on a Mac. So I decided to fix that by, well, first you'll find all the documentation in the Git. But what I did is to create a Docker image which kind of has all the tools, and you don't have to worry to take half a day to set up your system, or even more probably. You can also use it with Docker Compose. You just say, I want to build this project, and you can do it. The Docker image is actually on our container registry. And then you can do one magical Docker command, which you didn't see there because I had to fast forward this because it takes so long to build something. But in here, we're building two things with the microcontroller code, and we are synthesizing, placing, routing, and creating the binary file for the hello world, which kind of just turns on a LED. So a lot of things with just getting a blinking state out of this. Yeah, so, sorry. Kind of learnings, I tried to build a RISC-V core, and it turned out to be such a complex stack, and then I realized they use a different toolchain. So the toolchain used here is called SymbiFlow. There's another one based on GNU. So they're like kind of two options in open source FPGA toolchains. Also, you would notice that the SymbiFlow like open version is different than the one you have to use here. Like every vendor kind of has to personalize the toolchain at the end, and that kind of makes it a bit harder to follow these open source projects, because like manufacturers have different they have different versions of the same tool, and I'm not sure if they updated it like all the time. So yep, the RISC-V thing, there is open implementations that you can use. It's called Pupul. I think right now it's instituted in Geneva and in Italy somewhere, and you can find the implementations, and you can actually build a core in here. I couldn't get it to that level, but I think that it's promising that we could eventually do that and actually have some specific hardware that we might not be able to order in time or something, but we can just synthesize it here, and then we would have the hardware just by synthesizing and implementing an FPGA.